We're going to have Reem Mahmoud from VCU talking about 5 colorings of most 6 regular toroidal graphs being Kempe equivalent. Go ahead.
Okay, thank you. So I'm going to be talking about how 5 colorings of most 6 regular toroidal graphs are Kempe equivalent. This is sort of an overview of a paper that I wrote with Dan and Cranston. So I'll start by introducing a couple of definitions. The first one is for a graph G with a proper coloring phi, and alpha beta Kempe swap is done by exchanging the colors alpha and beta on a component of the subgraph induced by vertices colored alpha and beta. So for example, if you look at this graph right here, we've got a proper 4 coloring on the graph. And if we focus on the vertices induced the subgraph induced by vertices colored red and blue, then that would be basically this path that's highlighted in purple. And if we think about performing a red-blue Kempe swap on this component, then we would just switch the colorings on the vertices and basically get this coloring, which is still a proper coloring of the graph. And so any 2 K colorings of a graph G, say phi1 and phi2, are called K-Kempe equivalent if there exists a sequence of K colorings starting at phi1 and ending at phi2, such that every 2 consecutive colorings differ by a single Kempe swap. So that means if we can get from one coloring to the other by just performing a sequence of Kempe swaps, then both of those are K-Kempe equivalent. And I might refer to K-Kempe equivalent as just Kempe equivalent or K equivalent during this talk, because it's sort of understood that we're dealing with K colors. So let me give a little bit of sort of motivation for our work. We're often interested in sampling a quote unquote typical K coloring of a graph G, but counting exact combinatorial structures, in this case, the number of proper K colorings of a graph, is often a computationally hard problem. On the other hand, approximate counting may be possible if we use an algorithm which basically generates uniformly random proper K colorings of G. And so the way that this is done basically is we define a Markov chain on the graph whose vertices are the proper K colorings of G, and where 2 K colorings are adjacent if they differ by a single Kempe swap. And so in that case, reaching a uniform distribution is contingent upon the connectedness of this graph. And so basically we become interested in figuring out whether this graph of K colorings of G is connected or not, which ultimately just means whether the K colorings of G are Kempe equivalent or not. And this idea of using Kempe swaps is used in a lot of theoretical physics problems as well, and Markov chains like we explained, and other stochastic models. So here's what we do know. In 1981, Les Furness and Maniel showed that if G is D-degenerate, then all K colorings of G are K equivalent for K strictly greater than D. D-degenerate, just means that there's an ordering of the vertices where every vertex has at most D neighbors coming earlier in the ordering. And so an immediate consequence that we get from this is that all K colorings of planar graphs are K equivalent for K strictly greater than 5, because we know that planar graphs are 5 degenerate. And actually, Maniel extended that to include K equals 5 for planar graphs afterwards. So I'm going to be referring to this particular result a few times during the talk, and for that reason, I'm just going to call it the degeneracy lemma. So after that, Mohar showed that in 2007, he showed that 4 colorings of 3 chromatic planar graphs are 4 equivalent. And it's not too hard to show that all 3 colorings of bipartite graphs are 3 equivalent. So obviously, this also includes bipartite planar graphs. And so really, if we combine these results, what we're really saying is we're saying for a planar graph G, all chi plus 1 colorings are chi plus 1 equivalent, where chi is the chromatic number of the graph. And so the next question becomes, can we say the same thing about toroidal graphs? So here is what we know for toroidal graphs. We know that for K greater than or equal to 7, all K colorings are K equivalent, and that's just by the degeneracy lemma because toroidal graphs are 6 degenerate. When it comes to talking about 6 colorings, there are sort of like 2 results that combined give us what we know in terms of 6 colorings. So in that same paper of Mars, he conjectured that all K colorings of K regular graphs are K equivalent. And in 2017, Ferrari, Johnson, and Polsma showed that that is true for K equals 3, with one exception, which is this graph that you see on the right, which is the 3 prism. And then most recently in 2019, Bonamy and her co-authors showed that this is true for K greater than or equal to 4. And so Bonamy's result really tells us that 6 colorings of 6 regular toroidal graphs are Kempe equivalent. And if we combine that with the degeneracy lemma, then we have that all 6 colorings of toroidal graphs are 6 equivalent. And so if we do kind of the same thing that we did for planar graphs, what we're saying here is that chi+1 colorings for toroidal graphs are Kempe equivalent for chi greater than or equal to 5. So the next question would be, what about 5 colorings of 4 chromatic graphs? And that is what our main theorem is kind of going to answer sort of partially, because for starters, we focus particularly on 6 regular toroidal graphs. And what we're going to see is that most of these 6 regular toroidal graphs we're going to be dealing with are in fact going to turn out to be 4 colorable. So here is our main theorem, which says if G is a 6 regular toroidal graph with edge width at least 7, then all 5 colorings of G are 5 equivalent. And in order to kind of explain what we mean by edge width here, it's good to have a visual representation sort of the kind of graphs that we're dealing with. So 6 regular toroidal graphs in general fall into sort of one of these 2 structures that you see. So say for the sake of an example that we've got a toroidal graph, a 6 regular toroidal graph on 35 vertices. So it might look something like this structure on the left, where it's basically just a 5x7 grid, and you've got one-sided diagonals inside each of these squares. And in fact, what you can see here is I've actually got a 6x8 grid, and the reason is because this area that's shaded in gray is the actual graph, but this top row right here is just me replicating the last row over here. And this last column is just a replicate of the first column. And the reason I've put them there is to kind of show the adjacencies between the first and the last row and the first and the last columns. And the adjacencies in this case are sort of what we expect them to be. I like to call this like the standard structure, and we kind of denote it with T 5x7. The other possibility is that our graph looks like this thing on the right, which is basically the same as the standard structure, except there's what we call a shift happening between the edges between the first and the last columns. And so in this particular case that I've shown, there's a shift of 3 for the edges. And so there could be a shift of, any other, it could be a shift of 4 or 5 or anything like that. And it's sort of worth mentioning that the standard structure can actually also be represented as a structure having a shift of 1. So now that we know that our graphs look like something like this, what we mean when we say edge width at least 7 is that we want the length of the shortest non-contractible cycle to be at least 7. So that's what we mean when we say edge width at least 7. And so now I'm going to try to give like a brief outline of the proof that we use for this. So our proof relies on finding what we call good templates in our colorings of our graphs, and in particular finding something we call a good 4 template, which is something like you see here in this picture. The vertices colored in red, those form a good 4 template. And in general, a good 4 template is an independent set of size 4, such that identifying the vertices results in a 4 degenerate graph. So we can sort of see where this 4 degeneracy is going to be useful, because now what we can say is we identify the vertices of our good 4 template, and then we get this 4 degenerate graph. And so we can say by the degeneracy lemma, all 5 colorings of this resulting graph are 5 equivalent. And what that means in terms of our original graph is that any 2 5 colorings where the vertices of the template have a common color, those 2 colorings would be Kempe equivalent. So I'm going to try to give like a sort of hand-wavy argument for why identifying those vertices gives us a 4-degenerate graph. And the idea is that we want to find an ordering of the vertices or ordering of deleting the vertices such that every vertex that we delete has degree at most 4. And so in this particular case, we can start by deleting this middle vertex right here because 3 of its neighbors are identified into 1, and so its degree drops from 6 to 4. So we can go ahead and delete it. The next vertex we can delete is this one because 2 of its neighbors are identified into 1, and then it lost a neighbor right here. So again, it has degree 4. And we can keep going in this manner until we sort of reach a situation like this, where we have a vertex that's adjacent to, or that's got 2 neighbors that have already been deleted. And the idea sort of is that once we have a situation like this, we can go ahead and delete this one, and then every single vertex after that will have at least 2 of its neighbors already deleted. And so we can go around the whole torus and delete all the vertices, and then finally delete the vertices of our template. So that's sort of the general idea. So after that, really what our proof boils down to is just proving these 2 statements, which is the first one says that for any 2 5 colorings, phi 1 and phi 2, that each contain a good 4 template, those 2 colorings are Kempe equivalent, and that every 5 coloring is equivalent to some 5 coloring which contains a good 4 template. So I'm going to try to sort of briefly explain how we show the first statement. And again, it's going to rely on what I sort of briefly mentioned, which is that almost all of these graphs that we're dealing with are actually 4 colorable. So say we've got, like, say those are the 5 colorings that we're working with, or the 5 colors that we're working with. And say we've got those 2 colorings where each coloring contains, as you can see, a good 4 template. I've left out these vertices uncolored just to sort of highlight the templates. But we've got 2 colorings here, each with a good 4 template, and we want to show that they're equivalent. So the idea is the first step, we want to have a common color on both of our templates. And so let's just say I pick the color blue. And so what I'm going to do is I'm going to perform a bunch of chem swaps on the vertices on my template right here to just change the color to blue. So just do a red-blue swap. And then a similar thing for this template right here. So I get something like this. And so both of those are equivalent, and both of those are equivalent just by, just because all I did is I did a bunch of chem swaps. And so now here's where the 4 coloring comes into play. So here's our 4 coloring of the graph that we know exists. And we want to sort of introduce a 4 coloring which does not use the blue color that we used right here. And so the reason for that is because now what we can do is if we take any independent set in our 4 coloring right here and we color its vertices with blue, we still have a proper coloring. And so what that's going to help us with is basically what we're going to do is we're going to copy our template right here onto this 4 coloring. So something like this. And now by sort of what I explained in the previous slide, because these 2 colorings have this exact template in the same place with the same vertices, and the vertices of the template have a common color, both of those are equivalent by the degeneracy lemma. And so we can do a similar thing for the other template right here. And what that means is both of these colorings are equivalent to this 4 coloring through some chem swaps. So that gives us basically the kind of path that we're looking for, or the sequence of chem swaps that we need to do to get from this coloring to this one. And I'm just going to end it on this slide with like a sort of summary of the key points that I mentioned. And I'm going to stop here and ask if there are any questions.
So let's thank our speaker. Feel free to use a Zoom react or unmute yourself. Thank you. That was a great talk.
Sure. So just so that I am understanding, this is we have an infinite collection of examples that are not covered, right? Because we need the edge width to. In small edge width, you can still have large graphs. Did you do any computations to think about like how many equivalence classes there are in those like smaller infinite settings?
We did consider looking at that, this basically this possibility, but really our kind of paper focused mainly on just showing whether those graphs are going to be connected or not. So we didn't really focus too much on equivalence classes and things like that.
Thank you.
So you know that graph with the two like K2 times K3. What were the two different colorings that are not Kempe equivalent?
So basically that like three prism, let me go back to it. If you kind of draw it as like two triangles inside of each other, then kind of like just fix a three coloring on the outer triangle and then kind of switch the three coloring in for the inner triangle, and then both of those would not be Kempe equivalent, because any Kempe swaps that you would do basically would just kind of change the colorings on a whole color class. So you wouldn't really be doing anything.
All right, if there are no more questions, let's thank our speaker again.